Hello, Math 160. This is your pre-recorded lesson for Friday. We are going to take a quick look at a couple more examples of prime factorization and prime power factorization. So a little bit shorter of a lesson here. I just want to go through a couple quick examples of making some factor trees. Similar to what we were doing at the end of the last lesson here. So nothing too intense, but just kind of getting us used to this process of using some of our divisibility rules and writing out that factored form. So let's begin with our first example here, which is 693. I'm actually just going to move that over here into the middle. And then we want to look at this number and we want to, this is a small enough number, we can probably just use our calculator. We can start kind of dividing by different numbers. It looks like all of the digits here are divisible by 3. So this number should be at least divisible by 3. If your number is divisible by 3, you might also want to check to see if it's divisible by 9, which we can do pretty quickly by adding up these digits. So 6 plus 9 plus 3, that is 18. And then if we take 18 and we add up those digits again, we do get the number 9. So our original number, 693, is divisible by 9. And I always, when I'm working on factor trees like this, I always do suggest trying to divide by larger numbers because it makes the subsequent steps a little bit easier to work with, right? So 9 times 77 is going to be 693. And now I'm in pretty good shape. I don't really need to use my calculator anymore. I know that 9 is 3 times 3, and I know that 77 is 7 times 11. And then I'm done, right? I can't really break down these four numbers any further. Our four prime numbers that make up 693 are 3, 3, 7, and 11. So this means there's two ways we can represent the number 693. We can write it as 3 times 3 times 7 times 11. This is the prime factorization of 693. And I've also put those prime numbers in order. If I want to put the prime power factorization, I'm just going to collapse these two 3's together to get 3 squared. Okay, so we do 3 squared times 7 times 11. So this would be called the prime power factorization of 693. Okay, now I'm just using my calculator here to develop a second example for us to take a look at. And that number is, let's see, 115,500. So a pretty big number this time compared to some of the other numbers we've been using. Boom. But still a number that's easily tackleable with some of our knowledge that we know about our base 10 numbers. So looking at this number, it definitely looks like this number is divisible by 100. So that's maybe where I would start. I would take this number and I would divide it by 100, and that will give us 1,155. Okay, so 1,155 times 100 should give us that 115,500 that we started with. Okay, when it comes to the number 100, that one's not too bad. We can start breaking this one down in a pretty straightforward way. We know that 100 is 10 times 10. And then each 10 is 2 times 5. So each of these 10s can get broken down into one copy of 2 and one copy of 5. These are all prime numbers. So I'm going to go ahead, I'm just going to circle them in red. I can't really go any further with these numbers because they're prime numbers. They can't get divided down any further than where they are. Okay, now with a number like 1,155, to me, it's very obvious that it's divisible by the number 5. So maybe let's take a 5 out of there and see what we're left over with. Okay, and we get the number 231. So 231 times 5 would be equal to 1,155. I know 5 is a prime number, so I can't really break that one down any further. So what we want to do next is we want to think about the number 231. And like I always say, the easiest way to kind of start this is to think about adding up the digits, right? So adding up the digits generally gives you an idea of whether or not this is divisible by 3 or 9, which is a helpful thing. What do we get here? 2 plus 3 plus 1, this is 6. So we know that this number is in fact going to be divisible by 3. So let's take out that 3 and see what we have left over after we divide by 3. Okay, so we do end up getting 77, which is great. We've already dealt with the number 77. We know that 77 can get broken into 7 times 11. So all of the circled numbers here represent the prime numbers that basically get composed together to get our starting number of 115,500. So if we would like to write 115,500 in prime factorization form, we just list all of these prime numbers together. I'm going to do it in order. So we have 2 times 2. That takes care of that one and that one. We have, let's see, 1 copy of 3. We have 3 copies of 5. So boom, boom, boom. A copy of 7 and a copy of 11. So that should take care of all of the prime numbers that we found by creating this factor tree. Now, if I need the prime power factorization, I want to collapse some of these together. So I have 2 copies of 2. Okay, so we have 2 squared times 3. We have 3 copies of 5. We have 1 copy of 7 and 1 copy of 11. So this would be the prime power factorization of 115,500. Okay, so with that said, I actually don't have Moodle up and running exactly at this very second, but I do have a little bit of practice up on the Moodle page for you if that's something that you are interested in doing. I recommend doing a couple of these just to make sure you're comfortable. At least with 3 and 4 digit numbers, I think are very nice numbers to be able to kind of do mentally without having to use the calculator. So I just want to double check and make sure I have posted that for you. So under the working with natural numbers, so I have posted up the sieve of Eratosthenes. So I have posted up that new PDF for you to take a look at. And I have a little handout here, the prime power factorization worksheet, which has just a couple of 3-digit examples for you to try to decompose into the corresponding prime numbers. And on the second page here, of course, in red are the solutions. So yeah, so take a few moments just to grab a couple examples from the prime power worksheet. Try those out and see if you understand the concept of breaking numbers down into prime numbers. And then what we're going to try to be doing on next week on Monday and Wednesday is we're going to be trying to utilize the prime power factorization to find things like the greatest common factor or the lowest common multiple. These are concepts that come up quite a bit, especially when working with fractions or working with algebra when we want to factor things. So we'll discuss those key ideas hopefully on Monday and Wednesday, and that'll finish up this little chapter for us. One other thing that I did have inside of this little subfolder here is just a little blurb about an interesting property of prime numbers. Now, I don't necessarily think that it's important for you to know the proof of this theorem, but I think it's important that you know the concept. And the concept goes like this. Basically, the theorem says that the question is asked, how many primes are there? Are there 10? Are there 100? Are there 1,000? How many are there? And it turns out there are an infinite number of prime numbers. So that's what the theorem essentially says. It says there is no end to the number of prime numbers that we can find that are larger than the number 0. So there is a little bit of a proof here, and it goes through the kind of case-by-case scenario in a very algebraic kind of way. But what I've done on the back of this little handout is develop a numerical example to give you kind of an idea of how the proof goes. So essentially what we do inside of the proof to show that there are an infinite number of prime numbers is we do something called a proof by contradiction. So we kind of assume falsely that we can create a set of prime numbers, and this is all of the prime numbers. So for example, in the example that I've given here on the back side of the page, I've taken the prime numbers 3, 5, and 7, I've thrown them into the set, and I've kind of pretended that this is the largest possible set of prime numbers. So there are no prime numbers other than 3, 5, and 7. And then, so what happens if you assume that this set contains all of the prime numbers? There's one of two things that could happen. What we do is we kind of create a new number by multiplying all of the prime numbers together and then adding or subtracting 1. So in our case, we're going to add 1. That gets us to the number 211. And what happens is this new number we get by multiplying all the prime numbers together and adding 1, the addition of the number 1 makes sure that the new number we get is not divisible by 3, 5, or 7. And most of the time, this new number that we get is a prime number that's actually not on our original list. So we get this new number, 211. It turns out that 211 is a prime number that wasn't on the original list, so our original list was not complete. And it turns out you can just kind of keep doing this over and over again. So, you can create this brand new set by adding the new number that we found, 211, and then repeating this procedure of calculating a number 3 times 5 times 7 times 211, adding the number 1 to make sure that the new number we get, which is right here, is not divisible by 3, 5, 7, or 211, and then kind of checking to see if this new number is a prime number. Now, the new number we get, which is 22,156 with this particular example that we've started with, is not prime. It's definitely an even number. But what's interesting is we can decompose this number into prime numbers that actually aren't on the original list. So one of two things happens. If we pretend that we have a list that has all the prime numbers, when we multiply them together and add 1, we either get a new prime number or we get a composite number that's actually composed of prime numbers that aren't on our original list, which is, I think, a very bizarre and really interesting pattern. And the ancient Greeks actually knew of this pattern and utilized this pattern to essentially prove a long time ago that they knew that there were an infinite number of prime numbers. So you can kind of keep repeating this procedure. None of the lists that we make are ever going to be complete because we can always either get a brand new prime number or a brand new composite number that's composed of prime numbers that actually aren't on the list that we have. So that's the idea of the proof. We just keep doing that, so we know that there's no end to this procedure, so there must be an infinite number of prime numbers. So yeah, so that's there for you to kind of read and ponder about if it's something that you're curious about. And like I said, it's not something I'm going to ask you to prove, but I think it's something that's just nice to know. It's nice to know that there aren't a finite number of prime numbers. There's actually a lot of them out there. There's an infinite number of prime numbers, and people are still trying to find prime numbers to this day. All right, so that's really all I wanted to show you for Friday. We will get back together on Monday and Wednesday next week and talk about the two next key ideas in this section, which are the greatest common factor and lowest common multiple. All right, have a lovely weekend, everyone. Hopefully you get lots of lovely rest and then get to enjoy some sunshine. And we'll get back to the mathy things on a Monday.